Okay, so welcome back, everybody. I'm excited to get back going with these modules on generative molecular design. So what a perfect intro from James just now, telling you about all the real life applications and work they've done in industry. So we're really going to be looking at really under the hood, under the box versions of generative models. We went through a little bit of the intro parts yesterday and how important it is to build a latent space in order to design molecules and design fundamental axes that helps us have knobs to control in a mathematical way, such that you can do gradient descent to optimize towards molecular properties. Today, we're going to talk about more of this one use case, and we started talking about variational autoencoders yesterday. We are going to do some notebooks implementing that today, one for a set of like random discrete data, categorical data set, and a second one for a molecular dynamics trajectory. So hopefully these are things that you can take with you as you use in your own research projects. Let me go ahead and first share some slides. By the way, these two notebooks are in the day 5 repo. I think it's called like VAE example 1, example 2. The second example also pulls one. There's like a tar file from the data repo, but it also has a line that just grabs it, so you don't actually have to. But if you wanted to just be safe, you can download I just updated earlier today a new data set in the data repo that you'll load into the example 2. So we'll do that probably in the 3rd session. Okay, so let me go ahead and share my slides. Okay, everybody see that okay? That's good. All right, so day 2 for generative models and specifically variational autoencoders. So as we mentioned last time around, there's multiple types of generative models. Looked at VAEs being probably the most old school nowadays. Now GANs and specifically stabilized diffusion models is a lot more recent and usable, but I think from a pedagogical perspective, it's very useful to look at one of the more early stage versions of this, especially when you're working with chemical data sets, which are quite small. And so it's easier to take them. Plus, it actually uses the specific architectures that you guys looked at earlier for neural networks. So let me start as a review over this framework of this variational autoencoder as a quick review. So we talked about this architecture system of 2 neural networks, an encoder and decoder, that feeds into a latent space. So whenever you do just a regular feed-forward neural network, feed in input, for a predictive regular neural network, feed in some feature that represents your data set into a regular feed-forward neural network. The last layer is a latent space, some low-dimensional representation that then maps onto whatever label that you have. Here, we are not doing a predictive model. We are using unlabeled data. We care not about the prediction of the final output. We care about making that latent space, that last layer of your neural network, to be as representative, smooth as possible. I'll tell you more about why, like what that actually physically means. And then from that latent space, you can actually then use it as an input into a decoder, and then that can decode back into high dimensional space. We basically go into high dimensional space, use a neural network to compress things into low dimensionality. We make it low dimensional such that it's something that can be learnable, captures fundamental patterns in your particular chemical system. And if you find those patterns, then you can do some sort of optimization, like, maybe similar to what James was talking about. There's a particular set of properties for some chemical data set, and you can optimize towards like high, ionic connectivity or something like that. Then you can, point in a certain direction of chemical space rather than more like manual trial and error approach for searching a chemical space for a target property. So if you have a latent space that's able to do this, then what you can then do is just throw away your encoder and just use the rest. Basically, you just sample a point in your latent space and take that point back into real space, and whatever molecule that is, or whatever data point that is, then that will be in your high dimensional space. So that's the benefit of this whole variation autoencoder and really the whole framework of generative models as well. Something I'll also point out usually, so these are the encoder decoder are just neural networks. Usually they're symmetric. So and when you parameterize, but when you do backprop, you will have both parameters optimized at the same time. So you're not like optimizing one and then it's end to end. The full thing is constrained altogether. And it's not a hard fast rule or anything, but usually they're symmetric just for easier, because what you want to do is like lower dimensionality and then pull it back out. So naturally, however many number of layers and nodes you want to have in one is however many you want to have in the other as well. But all of these are, tunable, playable. You can adjust depending on your system and whatever optimizes best. And I shall also say, so, we started unlabeled data. We have this unsupervised learning process simply to learn a latent space. But you could then take this latent space and train this. So yesterday, we looked at a paper from Rafa Gomez Mamparelli, where we basically trained a model on top of this latent space that mapped to a predictive, in that case, there was a Gaussian process to some label property, and that's how you can optimize within this latent space. So basically latent space, which doesn't have any physical meaning, but then you can map that space to some physical property using another machine learning model. And that's how you can do a gradient type of optimization inside your latent space. And then sample points from that gradient decode back into some, chemical of interest or molecule of interest. Now let me say more about this. What is it that we do when we optimize? What is the loss function? We're trying to optimize this whole network. That loss function looks something like this. There are two pieces. One is this Kullback-Leibler divergence, and we covered this a little bit yesterday already. The second is a reconstruction loss, where that is really telling us if we feed in something, and then we go through this whole network, come out with regenerated for that same data point. We want those two things to be as close as possible to each other. So if we fed in this is the MNIST data set. If you handwritten 7, if you fed in this particular image, you want the output to be as close as possible. And then we're just really measuring how like some level of difference between that's your L2. So usually this could be like L2, just MSE type of error. We'll do an example for a categorical data set where we use cross entropy, similar thing, just basically how different is the true result versus the predicted result. And we talked about specifically this Kullback-Leibler divergence is a measure of how different two probability distributions are to each other. And that's really measuring the probability distribution that you learn from your data set. So when you come out of the encoder, you basically output a 2-column n by 2 array, or depending on the dimensions of latent space. So if you have, in our cases, all of our examples, we have just one dimension. I think the second one we have 2 dimensions, but you can tune that as well. But basically, there's only 2 values associated with this any one single data point coming in. That's the sigma and a mu and a sigma. So just the parameters necessary for a Gaussian. We just say, how close is that to a regular normal Gaussian? Like, what is the difference in that Gaussian? Is it a regular normal Gaussian shape? How far different is it? And this really provides a regularization type of approach to this loss function. So in addition to making your value try to match as best as possible to the output, your input value matches best as possible to the output value, this term creates the regularization that it makes the latent space smooth and organized. So yesterday we talked about these examples with like, we had like these like vegetables and some animals, and if you use regularization, you can have those latent representations be organized in those categories. Whereas if you had just, and that's the difference between a regular autoencoder versus the variational autoencoder. If you didn't have this regularization term, you can still do this one-to-one mapping in a parametric way, but you won't have that, it won't, like the spatial relationships within the latent space will not be learned without this regularization type of term. If we also choose this to be a normal distribution, and if you were to do so, it actually turns out to be a relatively simple algorithm, and we'll be using this in our code today. Okay, so that kind of gives us a quick review. Just before we get into the code, I just want to first tell you about like I think you guys have talked about this also in your previous neural network sessions, but just so, because we have kind of two of these things, so we have our input dimensions, we have hidden layers, and our latent dimension. Those are the choice number of layers. And we choose both the encoder decoder to be the same. So if we have 3 layers in your encoder, we choose also 3 in our decoder just to be symmetric, so that the amount of dimensionality reduction, the amount of information we reduce in going from high dimension to low for the input is the same we do for the output. Okay, so just some definitions before we get started. All right, so now let me move to the notebook. So this is going to be day 5. Day 5, example 1. Okay, can y'all see this okay? No? Can't see it? Oh. Maybe I should try sharing again.
No, we could see it, but I think the font was small.
Oh, it's small. Okay, maybe I'll just blow this up. Good to know. Yeah, because I'm on a 27-inch screen, so I think I probably have to.
Yeah, just zoom in a little bit. Maybe one more, and then I think we should be good. Maybe the students who have better eyesight can also give the thumbs up. This is good, actually.
It's good. Okay. Okay, this is like giant on my 27-inch screen. Okay. All right, so we're going to do this example first with the discrete data. What I mean by discrete data is categorical data. So like a classifier in sorts, except we're not doing a predictive model, but we have data sets I think it was 1024 data. I forget, but we'll see in a little bit. But each of those data points fall into a category. In this case, it's one hot encoded 32 categories, 32 classes. Our second example will be with a continuous data set. Okay, and also this example, by the way, is found in this very nice book by Andrew White, Deep Learning. But this is, I think this is a fantastic reference, by the way, for anybody who wants more info, more in depth for all the things that we talked about in this workshop. Okay, so again, this example is really generating new example classes from a distribution of possible classes. So in this case, the features are classes. So we have so this is a randomly generated data set, and each point is going to be a one hot encoding that tells you what class it's in. So in this case, we just made 32 classes. It's one hot, so basically a vector of all zeros, except there's one in one of those 32 cells in your vector that tells you which of the 32 classes it belongs in. So that's what usually you do for any type of categorical type of machine learning model. Here, we're not trying to make a classifier, but we just want to take in some feature and say what class it is. And they're unlabeled as well. So maybe you can think about also in your particular kind of research scope, if there are any applications that you might want to generate new data of some sort with some sort of categorical information. I think we saw some good examples from James on discrete types of data, but feel free to put in the chat if you have any thoughts on this. We can certainly talk about it later on. So in this case, we have a feature X that's going to, again, it's going to one hot encoding. And we basically want to learn the distribution from this data set such that we can generate new data points that is also some other one of these 32 categories. And so in addition to being able to generate new points, you can also learn a lot just from the latent space. So that latent space, just like all the things we talked about yesterday, we can use it not just for generation, we can use it for finding patterns, finding clustering, using it as a lower dimensional, less noisy input for other machine learning models. So the same way we did it for PCA-TC, UMAP and that kind of thing. The same as the last layer of a neural network, that's just a lower dimensional representation of your data. Yeah, and so then once you have this very nice latent space that you can train from our VAE, you can also then do optimization, which is great because if you have a discrete data set, it's not continuous and difficult to differentiate upon. But if you put it into a latent space, then it's continuous space. So that's another nice feature of this particular dimensionality reduction approach. Okay, so now let's talk more about this encoder and decoder, what goes into it. This encoder is, if you remember yesterday from our math notation, X is our input, Z is the variable we use for our latent space, X prime for our output. And so the encoder is basically saying, given X, what is Z? What is the probability of Z? That probability distribution that would take a one-hot encoding vector X as the input. And so we restrict that probability distribution to be normally distributed. So we want it to be that particular shape. And then that means that what comes out of that encoder is just going to be a mean and variance. That's all we need to define what that probability distribution, which we define to be normal, since hence the only thing we need is just a sigma and a mu to be able to define a point on the latent space. So you can think of it as like we input some large vector, some however complicated, maybe in this case, just this one hot encoding, output just two numbers, and that represents a point on the latent space. Well, not a point, it's literally a blob because you have this distribution in the latent space. And then I should also say that you can have higher dimensional latent spaces as well. In this case, we're going to use a very simple, in this particular example, we just have one single dimension of our latent space, but you could go higher dimension with more complexity. And you can also play with that parameter in this notebook as well. So then there's the decoder, which is the opposite procedure. We're going to say, if you have a Z, if you choose a point in the latent space, what is the X? What is the probability distribution of that X? And so basically you're inputting then this mu sigma that goes into the decoder. So just again, another Gaussian, and output a probability distribution. So the output is going to be a 32 vector again, with each point with some level of probability. So it won't be this like 1 hot 0 1, it will be a probability. So some distribution along that 32 that has some probability of each of those classes. We'll use a softmax at the end for the categorical. Then, and then we should also think about what kind of parameters we actually have control over in this VAE. So of course, the networks themselves, just like you think about the hyperparameters for all of the regular neural networks, so layers, nodes, all of that is tunable here as well. We do try to make, as I mentioned, we do try to make those two symmetric simply because it's usually the case you want to reduce dimension and then regenerate the same thing. So if you have more strength in one side or the other, that's usually a little bit unbalanced, but it's not a hard, fast rule. And yeah, and our encoder in this example is going to be just a mean and variance, which is a continuous variable. So we actually use a regression for that first part. The decoder, though, outputs a probability vector, and then we're going to have to use a softmax to turn it into one of those categories in this 32 class thing. Okay, so that kind of sets up our problem statement before we get into the code. So yeah, by the way, feel free to put some in the chat if anything's confusing along the way. Okay, so we're gonna go and start and load our several modules. So I think you guys have already used this in the last one. I purposely made everything PyTorch, and so that's compatible with all the other stuff that you learned. But yeah, just all PyTorch stuff, and then yeah, NumPy. Okay, so this data set's 1024 points, where each point is this 32 vector one hot encoding of a particular class. It's synthetic, and we don't have any labels on it. It's just whatever class this data point is in. So, for example, this one hot encoding is just some vector 32, and there's a 1 in one of them. So saying just what class it is. Okay, so we're just gonna define some variables here, just, number of samples, number of classes. In this case, we're gonna use our latent dimension of just one. This pedagogical example, we try to make everything as like show the code as possible, so that it's easier to see what's going on. The second example has a little bit more of using some more general PyTorch tools to handle data. But the first one, we're basically trying to just show as like clear as possible, less black box as possible. And then the hidden dimension 16. So that was just a choice here. Okay, so then this is just generating our initial data set. So we're gonna, make a synthetic data set. And what we're gonna do here is we'd like for our, our VAE to find some pattern inside of any random data set. So to prime it, we're gonna make a random set, but instead of just like random, 1 through 100 random numbers, we're gonna try to create two somewhat different Gaussian distributions, such that if there is a pattern, then the VAE can learn it. So it kind of primes things such that there is some organization, like two blobs of Gaussians from this random categorical data set, such that we can assess whether or not those two blobs remain during our regeneration and sampling from a latent space. So that's all this does. We just say, just creating random Z here, and then this is just putting two Gaussians together, basically. Okay, then we turn this into a histogram, or we create this data set. So basically this just, just histogram, so makes the edges of the bins. And then this is just a set of code that figures out of this random array of numbers, which bin does it fall into, so that we just have this final one-hot encoding of this discretized encoding. Now, you probably already learned this before, but in order to use PyTorch models, you have to turn it into a tensor object, PyTorch tensor object, and this is how you do it. Usually, you always have to have this float 32 set for this tensor object. So that's what we're doing right here. Okay, so if we just plot that array and what it looks like, what our synthetically generated data set looks like, that would look like this. So you can see there's 32 classes. This is just probability or how many there are. So you can see there's kind of two blobs, and that was what we're trying to do. We're trying to create something that has some distinguishing features to see if we can actually reproduce it later on with our VAE. So just random data set. Okay, so now we're going to build our encoder and decoder. And so this is using our the standard PyTorch way of building neural networks. I think, again, you guys have covered a large part of this, and I guess it was Wednesday or something. So, we're going to define two of these networks, one for the encoder, one for the decoder. We're going to combine the parameters together in just a little bit, but just so we can have these two separate networks, we first have the initialization, and here we're just having an initial input layer, and then that is just the 32, and then hidden dimensions, and then I think we set this to 16, and we have these two hidden layers with the ReLU activation and then an output layer. The output layer, we're just going to have our latent dimension earlier we defined as 1. So our output layer is literally just two numbers, a sigma and a mu, to define that Gaussian. Then we simply just pass our data through our network. So that's what this is doing right here. And then the output, again, is those two values, a sigma and a mu, except actually it's the log of the sigma that comes out here. And then because this is categorical data, and we'll show you, and I'll show you in a little bit that output shape, that, by the way, this is, the shape of this is going to be a batch size, because eventually, it's not going to be the full 1024. We'll feed this into the network by multiple batches, which you can define. We'll later define all the epoch and batch size and that kind of thing. But you can keep track of those kind of dimensions of that array later on. And then because the output of this is this 32 vector that is probability distribution, we want to then take that and turn it into, oh, sorry, that actually comes later. That's the decoder. Sorry, I was gonna say, okay, so this mu can be any number, but the sigma has to be positive. So we're actually gonna put the soft plus function and that make sure it's positive. Okay, so then we have a decoder function. And, you know, this is when we input the latent space value, so sigma epsilon, and outputs a 32 vector that is probability distribution of what class it should be. So it's symmetric with the encoder and the number of layers that it has. So same thing, you know, 2 hidden layers. And what comes out is this 32 vector. It's called a logit, by the way. So the initial thing that comes out is not actually the probability distribution. It's a raw score that is output by the model before we need to necessarily turn it into a probability. And so that softmax. So, you know, after, so basically this, you know, this is just initializing that decoder. Then here we are feeding, we're just inputting the data into the decoder, and then we use a softmax to turn it into probability distribution. All right. Okay, so that defines our 2 networks. Then we have the training process. So before we get to that, let me tell you more about this loss function. And we talked about it already a good bit, but so we have this 2 pieces. Loss. By the way, I think we've been calling the loss function. It's also called the ELBO, evidence lower bound. Don't know why you can call it that, but that's just name they came up with. This is just the loss function. It's the reconstruction loss function plus a KL divergence, the difference of 2 probability functions. I'm adding actually this beta term in front so that later we can actually tune this value to say how much strength we want to put on one or the ratio of how much strength we want to put on either of these 2 loss functions. For now, it's just going to be 1, but we'll come back to that. But the loss function is just balancing these 2 pieces. And that KL divergence, if we assume a standard normal Gaussian, it turns out to be this very nice analytical form that we can implement easily in code. You can also use more complex ones, but here for a pedagogical example, we don't need to. Okay, so then the output is just a sigma mu for a latent space dimension of 1. If you had a latent space dimension of 3, then you'd have 1 by 3 of those different, you'd have 3 mu's for each of the different dimensions of your latent space. Then the other thing is your reconstruction loss. So for continuous data, we usually use MSE, so just a regular L2. And we'll use that in the second example. But here, because we have a discrete data, we're going to use cross entropy loss, which is most commonly used for categorical types of data. And basically what it does is it says you have this one-hot encoding and you have the true predicted probability distribution, and it compares those and gets you an error. Okay, so one more thing before we move to the code is there's a thing called a reparameterization trick. So there was actually a very good question yesterday about, we can actually regenerate a data point from simply a PCA. Any low dimensionality, anything with low dimensionality, we can generate something back if it is parametric. So if it is a deterministic set of parameters like PCA, we have input set of parameters, complex function to low dimensionality, but because it's here, we just simply set of parameters with the mathematical function, we can go backwards as well. But we couldn't do that with a t-SNE or a UMAP because those are probabilistic. We have probability distribution, so it's not going to map back one-to-one to a single point, discrete point data. A regular neural network also, once you train the model, you have fixed parameters. You can also go back, but because we have this probability distribution in our latent space, when we sample from this latent space so I should first say there's 2 parts. One, first training the VAE, we're simply optimizing all of the neural network parameters such that we have a good latent space until, but once we find a good latent space, we fix the parameters. No need to do anything with them. then it becomes a model where we just throw away the encoder, sample a point in the latent space, and then map back out to a high dimensional space. The only thing is that the latent space is a bunch of Gaussians, so it's not really a single discrete data point, it is a distribution. And so there's this trick, and I won't go into the math of it. I think there's a number of resources for this as well. I'll link to this, I think maybe in the repo, but I just want to at least get you a conceptual idea of it. So if you have if you use a training point that goes into the latent space, that is a discrete point because it's one of your training data, you know what it mapped to. But then you add some noise to it, then it becomes a Gaussian. And then because of the fact that is now a Gaussian, because so basically what it looks like here is you have this mean that you fed in from your encoder outcomes and mean, and you just add some noise to your sigma, and then that distribution now can be sampled from your decoder. As opposed to just sampling the original Gaussian in itself. The reason for this is that this mu and epsilon originated from some input in your encoder. So you know what rough space that origin was in your latent space. And so this mathematically, it turns out that this is now differentiable such that you can do backprop. And so that's kind of the very general picture of things of this reparameterization trick. And so that basically allows you to map back out to a specific point in the sampling part. But there's more, like, I think a lot more mathematical origin of this. Feel free to look into that. You know, I can put some resources on that. All right, so now let's get into this loss function. So here we are simply defining our encoder decoder. So the functions we defined earlier up top. And then we're gonna set an optimizer. So here we're gonna combine both the encoder and decoder parameters, optimize them all together. Just as mentioned, we're not optimizing two separate networks. They're gonna be end-to-end connected and optimized all together. So just using standard atom optimizer. And then here is our loss function that we're going to define. This beta is that parameter I put in front of the KL portion, the Quebec-Liebeler divergence portion of the loss function, just to later on we can play around with this to see what happens if you bias one side or the other of that loss function. So for now, we'll just leave it alone. So again, from our encoder, we'll get a mu and a sigma. Then this is the reparameterization trick. That's a long one. And then we'll use our decoder to take that Z sample. So we'll sample something, and then we will decode it into these are again the raw values that come out of the decoder that we'll have to put into a softmax to add. And then we have our label that we convert for that one hot. And then this is our reconstruction loss. So we're using a cross entropy here. This is very standard for categorical types of data. So this is called the log likelihood, by the way. It's a very it's a concept that's used in many other machine learning algorithms as well. And then this is your KL loss, so that this is that analytical form that we're able to use because we assumed a normal Gaussian shape. We're going to just add those two loss components together, and we're going to print all three so we can kind of track which one, during the training process, we can track how each of the two contributions to the total loss is doing. So then we'll just go to the full training part. We're going to define a couple of parameters, just batch size 32, 16 epochs. You can change this around, but you'll see that they converge pretty well, pretty rapidly for not that many cycles. So this is probably sufficient. So we're just going to do two loops here, one over the number of epochs and then other over loop the batches. So one thing is we're going to randomly shuffle this the data set so that it's not going to be for each epoch. So that's not, the model can actually memorize the data if you don't shuffle the order of your data each epoch. So and usually people don't necessarily, so if you do other PyTorch models, there's data loader, there's like a more algorithm, like PyTorch has a better way of handling this, but I'm just showing you this so you can see like everything that's happening more explicitly. Next example, we'll use some of those tools. Okay, so then we're gonna loop here, we just have the batch, then, just dividing up the data portion for that particular batch size. Before you always need to clear out any residual gradients. The gradients can build up for these PyTorch models, so you always have to zero that out. And then this is just our loss function, so we can collect those 3 pieces that contribute to the total loss, do back prop, and then update the weights. So basically find the difference between the anticipated value and then just reparameterize here. So then we can just save the loss here so that we can plot it and we can see what's going on. Okay, so here we're just gonna plot all 3. By the way, I don't think I've been running each of these pieces, so just make sure I go through and run each of these sections so everything's updated. Okay, so then we'll just plot. And so this is all 3 components. So the total is the blue, but it's like almost exactly under the green, so you can't quite see it. Maybe I'll put this let's put this on top so you can see both. Well, I guess you can only see one or the other, but they're basically on top of each other. That's why you can't see it. And there's so basically KL drops really, really rapidly. There's that part becomes very optimized, but the reconstruction kind of hovers around. And then the total is the additive of the 2 parts. So if you were to tune that beta that we looked at earlier in your loss function, that again is really playing around with the weight of either getting as close as possible back, regenerating the data that you put in as close as possible versus regularization of learning something about the latent space. You can certainly tune how well these 2 pieces converge into the total part. We'll come back to this and play around with that. So once we have this trained, then we should evaluate it. We should, because basically once we've optimized the network, all the parts are frozen. We no longer need the encoder because the encoder was only present such that we use both encoder decoders to try to optimize the latent space. Now we don't really need it. The only thing that really is valuable is that decoder because it takes in information about some latent space value and then can get back out some high dimensional representation of your data. So here we're just gonna, because we have a categorical synthetic data set anyways, we're gonna simply sample the same number of data points we started with, 1024, but just random numbers, just a bunch of random numbers that don't, if you had, for example, some real chemical set and those latent space points represented had, you can find patterns within them for some particular property, some viscosity of some liquid or something, and you can purposely choose certain regions of your latent space to sample, then that's what you should do. But here we're just simply taking a look at what is in the latent space from a random sampling like this here. So then we just feed this random set of numbers in the latent space to the decoder, and then that's going to pass through decoder, and we're going to get a probability. So this PX is a probability over those 32 categories from a softmax. And then we simply take those and take that softmax probability into what actual category, like singular category, one of those 32 classes is going to be. And you might think like, okay, maybe if we had like this vector of this, if this was our probability of like the 32 vector, then we just always pick the highest number as your whatever class it falls in. But remember, we're doing this for 10, 24, where instead of always taking the highest probability data point, we should actually sample the whole distribution. So, you know, 1 out of those 1,000, or like 10 out of those 1,000 data points, there's gonna be class 1 instead of class whatever number this is. So to do that, we use this multinomial thing that does this. So basically, we're not just picking the probability that the class that associated with the highest probability, we're using the probability distribution to actually pick the class in this case. And then just formatting wise, we can turn that back into a one-hot encoding, so we can plot easier. So then, yeah, so then we'll go back to this one-hot, that's what gets returned. So then we just, you know, use this function, get our samples. That's just this one set one-hot, so we can just plot them. And then that will look like this. So should I run this as well? So this was the original data set that we had. So we can plot both our original training set. You can see it was this like 2 Gaussian-ish distributions. Then we trained this combined encoder-decoder setup. And then using this training set where we tried to reconstruct all the training points, all these points, and their we tried to reconstruct those points while creating regularization. And then once we fix those parameters, we use the decoder to feed in just 1,024 other random data points and try to generate what that distribution looks like. So basically, we're trying to recreate the latent space here. And if we learn the latent space well, we should get a good distribution, similar distribution to what our input distribution looks like. And I think that pretty much, you know, we can see the 2 peak situation. I mean, it's not going to be a perfect one-to-one match. We have this dimensionality reduction step in the middle, but because of the fact we learned a pattern in the latent space, we get distributions that are quite similar here. Okay. So then, okay, so this is basically kind of like a regularization check, because if we found patterns if we found a latent space that recognized the overall pattern, then we achieve the rough categories or rough you know, larger scale pattern of the original data set here, which we did. But we could also check a reconstruction as well. So the 2 parts of the real loss function, we're basically doing 2 checks, one on each. The second check is on that reconstruction portion. So this, let's say we just take 1 data point from our training set, and then we just take that 1 data point from the training set, put it into the encoder, take that mu sigma and take it out the decoder and see what the difference is, right? Basically, what we fed into the VAE, does it spit out the same thing we fed in? So that's what we ideally would want. And so that's what this part is doing here. Except remember, the output is going to be a probability distribution. It's that 32 encoding with probability distribution. And so what you see here, so the input that we originally put in is this orange line X, and what came out of the decoder is this probability distribution. You can see it's not very good. It's like maybe there's like 2 rough regions where we think this point would be, maybe around 25 and 12 or something, but it's not really, like, it doesn't really predict. So you know, what it would be a good representation would be if you had a peak that nicely centered around your original line. Basically, it would be saying this had the highest probability. It's not the case, but it's not wrong, entirely wrong there. Maybe there's some density in this area as well, but altogether, this is not very good. So what this is really kind of saying is that we're doing a good job of regularization, but we're not really doing all that great of a job at reconstruction. As in, for singularity points in our training set that we, you know, part of the loss function is to do this, is to input something, try to regenerate the same thing in this 1 single check where we just literally chose some random number, some like random, this is the 3rd sample in the data set. We didn't do a great job of this. So now we can think about all the things that we have control over in this variation. So this is kind of the end of this first example notebook. But I like maybe for y'all to take a few minutes to think about what are the things that we can do to see if we can make this situation better. So think about the variables you have control over, the latent space, that beta value of what the KL loss and reconstruction loss is. You could change the parameters a bit, but the neural network parameters a bit. I'm not sure. I don't think it might the shapes of things I think are largely not hard coded, so you can play around with that as well. But I figured it would be good for y'all to take a whack at that, and then we can come back together and talk about it. Feel free to ask any questions also in the meantime.
Shuwen, there are two questions in the chat.
Okay, gotcha. Sorry, I gotta open up my Zoom windows here. So the first question is, if we assume that PZ is a Gaussian, does that imply that Q, so the binary probability of X, Z given X must also be Gaussian? Be incorrect. So we do assume, we assume what's in the latent space is Gaussian. And so we assume normal Gaussian in the latent space, and we basically try to see the Gaussian shape of what comes out of our encoder, how close that is to that latent space, normal standard Gaussian. So that's what the KL is measuring. So I guess the question is really, could this assumption be incorrect? I mean, that's a good question. It may be something very system specific if so the Gaussian part is really just to make your data set smooth so that you have a continuous variable in your latent space such that you can move around it using gradient optimization, and less so what necessarily is your data. But it could also be the case, you know, if you had some very patchy data sets in a latent space and there are parts not well covered. You know, I suppose a Gaussian doesn't always have to be the best approach. So does that help? Feel free to comment on that. Then the second question is, so we're seeing X showing up in the wrong place. So yeah, so this orange line. And so like which of these is wrong, if I'm understanding the question correctly. So X is the training data point, so we're plotting the training, the original data point where we know we know that this point that we fed in is in this category, I guess 14, class 14. And then we went through all the encoder and decoder to then predict what is the probability of this point being in any of these classes. And that it predicts a probability being in 14, like not that high, predicts it more likely to be here or maybe even here. So the blue is the variable prediction. The orange is the ground truth in this case. So we have an input that we know is in a certain category, and then the blue, this is the reconstruction. We're trying to basically, you know, kind of like that MNIST example with the hand drawn like numbers, like if you fed in a 7, what looks like a 7, you want to come back with an image that also is as close as possible to that hand drawn 7. This is the blue line is our analogous version of that. So it's not doing a great job in this case, but there are things we can do to tune this around and make this better. Okay, so maybe I'll just then now play around with that part now of parts we can tune and see what it does. I don't know if anybody's played around and saw anything already. Feel free to put that in the chat as well. So I'll say the very easier thing to do is to play around with this beta value of, let me actually go back to this equation. So you can see that we have a parameter of control over what is doing regularization and what is doing reconstruction loss. So this reconstruction loss is what is controlling this, like how well our prediction of how well our output probability prediction of the original thing that we fed in is. So like again, we don't have any labels, but when we look at reconstruction, it is a regression-based approach. We have input, and that is the ground truth answer. We go through the model, and we want the output to be exactly the same as the input. So in that sense, we know exactly what the answer is because we just want to recreate the thing that we fed in. And so this is a metric of what that reconstruction part is. One example of it, at least. We have, we can sample 24 points. So we could very easily just tune this parameter and put, let's say, less weight on your KL divergence and more weight on your reconstruction and see if we can play around with that balance a little bit more. So let's go back to, so this is just in the function, but let's go back to the training part where we set the beta value right here in your loss function. So we can make this a little bit smaller. So maybe we'll do like 0.5. And we can go through training again. Plot our loss. That looks about the same. And then take a look at the valuation. Maybe it's a little bit more different than before. Remember, if we're making our KL smaller, then we probably will have these distributions become more different because then we can't quite find the patterns of the overall set as much, or the organization of the data. Then if we try this, this certainly got a little bit better. So now we have our original data point, and now our prediction is our prediction from probability distribution is much closer to what we anticipated it to be. We can play around with that a little bit more. Maybe we can even make it even more extreme for one side or the other. Maybe 0.1. Plot our loss again. So you can now see a good bit of a difference in that loss function. So total is the orange, that's your total loss function, which is the additive of the KL and the reconstruction loss. And now you can see they're kind of more balanced, right? So before, I think KL just like sank to 0 right away. It was optimized like in just a few steps, and the reconstruction wasn't really going down all that much. But now we can see a bit more of a balance here. So then we can evaluate that distribution again. I mean, still fairly similar, like what we trained, what was in the training set, was in our, this is again, just sampling 1024 different data points. Maybe the shape gets a little bit more noisier compared to before, but altogether pretty good. Then we can do reconstruction again. And then now we're pretty much spot on. So our probability, predicted probability of what the input training set input would like reconstructing that training set input is pretty much exactly as what we anticipated it to be. So now we're hitting it exactly. So I see there's another question here. We're choosing different points. What we anticipate? Okay, so maybe that clear things up. Yeah. So yeah, so now we're basically really more optimizing this reconstruction part while not really sacrificing much of the generalizability as well. So that seems good. I mean, we can push this maybe even more. I don't know, I haven't even tried smaller numbers, so I don't know what this will look like either. We'll see. But you can see this one parameter we can tune and what kind of things it can prioritize and how you can optimize certain objectives in your loss. Okay, so now the loss looks a lot higher, so I'm anticipating something will not be like the KL isn't really converging much at all. So here, we'll come back. Okay, so now this is our original training set. This now is our generated. So we basically have not really learned the latent space. So basically, like, this is now the case when we had that latent space, we're gonna have like our animals and vegetables all mixed up. It didn't really learn the organization. Maybe we can still get the reconstruction really well, but we certainly, okay, reconstruction now is like excellent, because we really put all the weight on that part now, right? We have this probability density exactly matching our initial data point, but we've lost a lot of information about the overall organization. So if you remember yesterday, we had that latent space with like animals and vegetables, and ideally like all the animals would be in one region, all the vegetables would be in one region. And even if they were all mixed together, you can still get really good reconstruction loss. You can still like have an input feed into a certain point in your latent space, come out, and then regenerate the same thing. But that can happen while not learning the organization of the latent space if we don't put enough priority on that KL divergence loss. So that's what's going on here. So basically we have no regularization in this case, or not very much regularization in this case, but we can get perfect reconstruction loss. Okay, so I see a few more things. If I don't have label data, how to set beta. So it's a good point. So all of this is unsupervised learning. We don't have any labels. There's not a prediction, but the reconstruction part is kind of a supervised learning part, in the sense that we have an input and we're just recreating the same thing we fed in, because we have this low dimension, go back to high dimension kind of comparison. That's what reconstruction is. So the beta is really more so sensitive to the types of data sets that we have. It's more empirical. I suppose you can think of it as a hyperparameter in this case, but it's also a choice of, similar to how you guys have looked at those like ridge and lasso models with regularization, a similar thing, like how much regularization you want to put onto these models. It's a very similar phenomenon, and you may want one or the other, depending. For example, if you have a chemical data set of molecules Q of 9 or something like that, and you want to have the latent space be smooth enough such that you can sample, you can like do gradient descent and be able to optimize for a certain predictive property, then you might want the KL to play a bigger role in that case, such that you make sure you have something very smooth, generalizable to use. But that's more of an empirical playing around with those parameters. So that's kind of what my opinion on that is. Then I'll see somewhere else. If your X sample is at a lower probability value, will your P of X be less compelling? Not quite sure. Could you clarify what your question is? Do you mean if you change I, do you mean if I choose another number? So like if we just choose a different number? So this is just like a random sampling of points. So yeah, it doesn't work all that great for everything, I guess. So maybe if we just choose the first point. But yeah, you can certainly play around with this and see how optimal. For many of them, it seems to be spot on. For some of them, it's not. But you can certainly play around with it. So this one is like not very good. Yeah, so there's some like cases you're not going to get a very good reconstruction. Great question, though. You can certainly see these differences. I mean, we could also make this KL a little bit less strong and see. There you go. Because if the latent space is not learned well, I mean, it's not necessarily just like a good balance between the two, I think is the most ideal situation we want. Yeah, I mean, some of the data points appears just, it could be, one of those more spotchier patches on the latent space that isn't close to the other points, and it's hard to generalize to those areas as well. So, yeah. Any other questions? Did anybody test the latent space dimension? So we can play around with that as well. I think this looks a little bit better compared to the single dimension. So this is still at the beta 0.1, but with dimension, latent space dimension 2. When we can get that prediction pretty well here for that 8, which is causing problems earlier. Yeah. Yeah, so another thing that you can play with is that latent space dimension, and then you can also play around with the neural network sizes as well. It's not a large data set though, so you can't really go too large. It shouldn't really change all too much, but yeah, something else to play with. Also, I know we're probably supposed to take a break at the end of the hour, which we passed. So perhaps we can do that now and then move on to the second example after that.
Yeah, I think it would be good to take the break, maybe 5 minutes.
Okay, sounds good. Feel free to put more questions in the chat for everybody else. Okay, so let's get back to it. There's another question in the chat, so I just want to address that now that we're all back. So back to that, whether or not the P of Z being Gaussian, or whether Q of Z should also be Gaussian because P of Z, whether Q needs to be Gaussian because P of Z is a Gaussian. So I first say I'm not certain because I've only seen the Gaussian situation, but I will say I think if there's nothing a priori setting Q to be a Gaussian except for easiness. So I think it can be anything else. And I guess if you have your true distribution is like multiple peaks or something, then approximating that as a Gaussian would not work well. So that's kind of my intuition. Okay, so that's a great question. Okay, so this is also, you can go back and play around with this however you would like. I'll now move to a second example that is, we're going to do very similar processes, functions, but for a more chemically relevant system. So let me change over back to the slides. So now we're going to do an example on instead of a random data set categorical, now we have a continuous system of a trajectory from what would be a molecular dynamics simulation. So in this case, a bead spring polymer. So you have some beads around and in a polymer, by harmonic springs. Some of you might have already done similar kind of simulations. And so you can imagine collecting just, and we're gonna simplify things, just 2D XY coordinates over time. So your data set is frames by 2, just XY coordinates by number of particles. In this case, we have 12 beads in your system. Just one quick thing before we move to the code is that we're going to also apply translational and rotational invariance. So if we just use the raw XY coordinates, if we were to rotate this polymer system or translate it by they give different numbers, but we're still having the true coordinates the same. The same if you would do like like a smile string is agnostic to however what the actual coordinates are. So because we have XY coordinates, and the same is true also just in general, when you have chemical inputs based on the structure, you featureize it to usually try to remove any sort of rotational, translational, and permutational invariance. For example, if you have a water molecule and you have HOH versus OHH and the coordinates associated, you want those to be the same because they're technically the same, nothing changed. But because it's read as a data input in a sequential way, in a vector form, then the machine learning model might interpret that as a separate thing. So we have to basically transform any inputs that have these differences in such a way that it can read these molecular chemical types of data sets without assuming that they are in fact different things. Although I will say, I think in the more recent types of models, like these LLM type of prediction foundation models, it seems to be the case empirically, at least, that simple non-transform trajectory and XYZ coordinate structure information can still be read well. So maybe that's changing. Maybe there's like more advanced models that can handle these things nowadays. But if we stick with these more simpler models, usually you have to do some of these transformations. Okay, so now let's move on to the code. This is called Day 5 EAE Example 2 in the repo. Give me a sec to go to setup. Blow this up again. Okay. So we're going to do a very similar example, building another VAE. I'll point out the main differences. Otherwise, the architecture, I think, is like not that different from the example you just saw. But I'll point out some of the differences, especially in that we now have a continuous data set instead of categorical. So we don't have to, like, for example, the decoder no longer has to have that softmax at the end for converting over to a particular probability distribution of those 32 classes. And it's more conventional than to use that reconstruction loss as something like an MSE or L2 type of difference for reconstruction, as opposed to we use cross entropy for categorical data earlier in that first discrete data set. Those are more or less the main differences. And then we also used some more native PyTorch tools instead of breaking things down from scratch. And I'll point those out as we come to them. Okay, so our system here is a trajectory of a simple 12-bead polymer chain in 2D space. So basically it's a frame trajectory. So basically you have, so this array of input is 3 dimensions. Each data point is 12 beats and the 2 coordinates. So it's 1 frame of a trajectory, and then you have n frames. Oh yeah, so I should have mentioned this earlier, but if you haven't already, so this should be able to get you the data set we're going to work with. But if not, I have also uploaded it. So, run it, and I've had no problems with this. I assume it should be fine. But if you happen to, I put this inside of the, actually I have the long one. Was using the right one? I have the downloaded one in the data repo as well, so you can download it just and upload it in here if you need the. Okay, so this is just that data set, and then we're just loading it into XYZ as an array. So this set of functions is simply that translational and rotational invariance I just talked about. We're removing any translation. And so like if you have these XYZ coordinates and we rotate and move it like as a rigid body, moving it in any changes in absolute environment, we're removing those differences such that the machine learning model reads them as the same. So we're basically just aligning our data by changing those initial XY coordinates into ones that are no longer, that are invariant to rotation and translation. So this is still the same size. We're rearranging the numbers a little bit, but it's still the same size. It's n by 12, b's by 2, the 2 XY coordinates. So first we can just take a look at that trajectory. So we can just visualize that trajectory. So here plotting all the frames. So each one might be like one of these squiggles, and then they're just on top of each other in this particular case. Just so it looks like this, but they're just XY coordinates of your one single frame, all stacked on top of each other. We can just take a look at one of them as well. Might look like this. Take a look at a few, but basically they're just samples of this trajectory that's happening. Then, okay, so now we can take a look at maybe a more analytical way of assessing this random trajectory or random bead locations. So if we were to just collectively count the pairwise distances between bead, so if you were to number your beads 0 to 11, since it's indexed at 0, then you can find the pairwise distances between that first bead with X number of beads. So the beads that are closer together tend to sit closer together, and then the beads are further apart tend to sit further apart, although you should have higher variance as they sit further apart. So their connection, this is their bond distance from each other. And you can just take a look at the rough distribution of things for this training set that we have. So yeah, so you can see this spread between the two beads sitting next to each other. So bead 0 and bead 1, they're very close to each other on this x-axis. And then if you have the next neighbor bead further away, then that distribution is a little bit further spread out, and so forth and so forth. But once you go to these further spread out beads, they wrap around a bit, so they do get, it's a larger distribution altogether. This is just, we're going to come back to this because similar to our first example, we had a distribution of our initial data set in a nice histogram. It's hard to do that from just the raw trajectory, so this is a little bit easier for us to compare what is the distribution of our initial data set. So we'll come back to this to see about, that generalization / reconstruction part if we can get back to this piece. Okay, so in dealing with that data set, we are simply just flattening it. So it was n by 12 by 2. We're going to flatten it into 24, so a single 24 vector to feed into the VAE. And the rest of it is going to be very similar to what we did with our other VAE with just the synthetic data set, because it's just vector of 24, vector of 32 as before, very similar, except this is now a continuous data set. So if we run this, okay, so you can see 24 dimensions. Just as before, we have to convert our NumPy array into a PyTorch tensor object to be used for a PyTorch model. And then here we're actually going to use this data loader. I think you were doing this also probably in your Wednesday sessions as well. We're going to use the data loader to deal with all of the batch sizing, shuffling in a more efficient way than we did in example 1, where we define all the batches, the shuffling separately in that loop. We're going to let data loader handle it. It's the same thing, but more efficiently. This is, by the way, just a PyTorch thing. Okay. Okay, so then we just build our model once again. This part is relatively self-explanatory, given that we did very similar thing before. We're going to define our input dimension. So this is 24 vector this time around, 2 dimensions, larger hidden dimension size, but you could vary this as well. We can maybe come back and play with this, see if anything changes. Yeah, so we define that, and then we just define our encoder, decoder. So most of this is more or less the same as before. So this part, nothing different. The decoder no longer has that complex, not that complex, but more involved, changing from a raw logic to the softmax for the categorical class 32 class thing. We're just getting the raw value here. So basically what is going to output the trajectory raw value here. So basically the XY coordinate of a frame. By the way, we haven't touched upon this, but we could, this is a bit more complex of a data set than that, single dimension thing we had earlier in the first example. So we haven't really messed around the number of layers and such. So these are all things that can be tuned and played with that, could influence how well the model performs. So we'll go back to the loss. This is very similar. So yeah, same as before, we define our encoder, decoder, optimizer for both the encoder and decoder all together. Just have this full end-to-end optimization process. The loss here, so encoder will get this mu and sigma in the loss, and then this is the reparameterization trick and get the decoder, but we're going to use an MSE for the loss here. So this is basically assuming a Gaussian with a fixed variance, which is not always true, but in this case, we're just to make this approximation of this particular Gaussian with a fixed variance. Makes things a little bit less flexible, I suppose. But this is, something that is often done for continuous data sets. And this is different in that we were using cross entropy earlier for the discrete data set. You can also define flexible Gaussian with not fixed variance also. It'd be a little bit more complicated, but you can also define that as the reconstruction loss. And then the KL divergence term is the same. And then same as before, we will spit out both the loss contributions as well as the total loss contribution. So then we'll get over to the training part. We're going to find 20 epochs and use the load batch loader part for the batching. And that all is a bit more efficient than our manual way of doing it earlier. And then, the rest is the same as before. We're going to zero out the gradient first, and then use the loss function. Okay, so I don't remember let me go back to this one first, and then we'll see about changing these variables in just a sec. And did I run this one? Okay. And then so that's training, and we're storing the loss here, and then just printing out each of the pieces. So we can actually print that here. You can print the loss function, so you can see the KL just kind of initially just flattens out, and the reconstruction does go down. This is a bit of a strange shape going on over here at the top. Don't know what's going on here, but it does starting to flatten out a little bit later. And then I imagine if we were to change that beta value, we'll see some more of a balance between these two components contributing to the total loss. But let's see what happens in this first pass. Okay, so just, for a quick check, maybe we can just generate a set of random configurations. And this is just randomly sampling, just like we did a similar thing in the first example. We just sample some number of points from the latent space, and then decode it, and then just plot what they look like. Here's what they might look like. I don't know if they look all that similar. They look, if we compare it to these kind of things, I would say they look kind of different, right? These look more jagged, and this seems smoother. There's some like roundedness to it. So we can certainly see something isn't quite great about this particular reconstruction. And not reconstruction, we're not matching what, we're just sampling random data here, but something about the type of, trajectory that we're spitting out isn't quite what it looks like in the original thing. But what we can do then is just replot that set of distributions we were looking at earlier so the blue is what we plotted earlier of that distance between each of the bead spring beads with its nearby neighbors. So this is that first nearby neighbor and then stretching out to the seventh, or I guess 8 bonds apart neighbors and what their distances are. And then the red is what we sampled. We can then sample, in this case, like 1,000 different snapshots. And from our using the latent space sample like a large data set and see if we can get close to what our learned original data distribution was. So in this case, not that good. I mean, it looks like, yeah, maybe the shape doesn't look particularly well. So we can maybe now go back and play around with what kind of parameters we can change to improve upon this prediction. Okay, so maybe I'll maybe take a sec and let you guys play with it a little bit and see if you find anything interesting. And I'll be playing with it at the same time. And then we'll come back and talk about it together. All right, so I don't know if y'all had some time to play around some of the parameters, but maybe we can now come back and talk about some ways that we can influence the distributions that we can generate from sampling in the latent space. So I'll just tell you about first some of the things I tried, and then if anybody else tried anything else, please feel free to put it in the chat or unmute yourself and talk about it as well, or have any questions. So I played around with two things, or actually a few things, just the latent space, hidden dimensions. I didn't change the number of layers. I think it was already 2, but I played around with more, and it used to be 256, and I made this less. So basically make the network smaller, which I don't think I forgot, maybe I changed more than variable at one time. I don't think changing the hidden dimensions changed all that much, but increasing the dimensions earlier got a better fit. And then I changed the beta down to 0.05. So this is making the KL a lot less smaller ratio compared to the reconstruction loss. And then you can kind of see a more of a balanced loss between those two terms in the loss function in this function here. And so then I mean, even visibly, it seems like the trajectories look a little bit closer to what we were generating, what we had in our training data. They look kind of, you know, more sharp in shape form. And then this is about as close as I could get to, at least by changing those parameters in a manual way. So you can see like the distances between 0 and 7. The shape is more or less there, is a little bit shifted, but as we get closer to this smaller distance, so beads that are closer together in that polymer chain, which seems like we can't really get very close. And that could also be because our data set simply doesn't really have we don't necessarily, we may not have enough a good latent space distribution that showcases this part. Because I imagine those two beads are like not moving very much, whereas your 0 and 7 are like all over the place, and you can sample a bit more wider breadth of your latent space, whereas like those two beads next to each other are like, you know, torsionally constrained and all of that. But in any case, can't really get very close on this closer bead situation, but you can get closer distributions or from your sample data points compared to the raw original data points. So here we have another question. The output of the decoder in comparison to the previous example from the decoder appears that we are reconstructing the input variables directly, but the top and output, there's going to reinforce the P of X given Z should be normal. Based about how that constraint is enforced. So the decoder, I'm not sure if you mean the encoder, the output of the decoder. Well, so the output of P of X given Z, the output of the decoder is simply just like, we don't have to do the categorization compared to the previous example because it was a discrete data set. If that is the question you're asking here. The previous example, so actually I have it pulled up here. You can take a look at the decoder differences here. So we had to softmax this because of the fact that the raw values are the like raw scores that are still qualitatively still representative of which of those bins of those 3 or 32 classes are more likely, but we softmaxed it in this case for the categorical probability distribution, which we then later did a multimodal thing on in order to identify a single class as we sampled those 1,024 new points. Here we don't do any of that. Where is it? So here we have this continuous data set, so we don't need to do that basically. Oh, but you were saying something about the beginning of the notebook, maybe I'd make that clear. Yeah, so, okay, yeah, this is a good point. So, this, the PFX given Z should be normal. And, we could use, like, we could have, implemented this negative log likelihood. We here, in this particular example, though, we just used an MSE, which has that fixed Gaussian variance. So that is an approximation, and that we're not using the true negative log likelihood version of this. You can do that, we can implement it. I don't think it'll make too much of a difference for this data set, small anyways, if that's the part of the confusion you're asking about. Okay, there's another question. The hidden layer dimension is higher than the input dimension. Would it be better to decrease than increase compared to the input dimension? That's a good point. You're right in the sense that like these networks, it's in some ways dangerous to make them very, very high dimensional. You can overfit easily. So we can certainly reduce these things down to see. It's not so much the comparison to this input, because you can have very, very large, it's 24 in dimension, but it can be very large in the data set. So it could still require this dimensionality, but it's more so, I mean, I find it, at least personally, more of a trial and error play around to check when we don't actually print. We had this like unlabeled data set, so we don't really, we can't really visualize like a test train overfitting situation. It's really this final loss reconstruction that we use to evaluate how well we're able to do here without overfitting, the balance between this regularization and reproducing that original input reconstruction. But that's very much a tunable parameter to try around with. Maybe we can try that now and see, like, if we just, I don't know, make this like 16, if that changes things too much. It's always good to use a smaller model when you can. It's a good suggestion. More or less, I think, is the relative loss values as earlier, I think. I think it looks about the same, right? I don't think we've lost any accuracy, if at all. So it seems like that hidden layer size dimension didn't need to be that large. So great suggestion. Well, there's certainly things more to play with in the parameter space. So feel free to let me know if anybody else tried anything else. In the meantime, I'm happy to answer. This wraps up the VAE session. I think it gives you an introductory level template, at least, of how to build one of these things, how to implement it in PyTorch, and ways you can affect the parameters for what you want. The more broader use case of this is if instead of, because all the cases we did, we just like randomly sampled the latent space. The broader use case for inverse design, molecular design, is to train something on top of the latent space. So instead of just the latent space, you map it to some physical property. So none of this was a prediction model. It was all for optimization of the latent space, or rather for making the latent space smooth, and also generalizable, but good at reconstructing an input to an input and output in and out of the encoder and decoder. But the trick to making this work for inverse design is if you can map that latent space to a predictive property, like each of the points in the latent space being associated with some property, some molecular space of interest, and then that organization of your latent space can say something that is useful about what kind of what categories of molecules or what categories of trajectory kind of conformational information is most associated with XYZ property. And then you can then perform optimization using, you can basically, because you're basically sitting on a gradient on top of your latent space, and you can optimize for more like a certain property value and back out what point it sits on the latent space, and then use the decoder and generate out what molecule it is or what configuration it is associated. So that's kind of the the framework that people use for this inverse design process. And here you have one of the key building blocks towards that. Okay, so we have another question for the autoencoder fraction of variational explained or FVE metric used to set the latent dimension. Can we use that for Van? Could you clarify that question? I'm not clear what you mean. Okay, so I think we, if I'm understanding correctly, yesterday we went over some other dimensionality reduction mechanisms where we had this, what was that called? This, basically how many PCs we could have, right? And that told us the number of latent dimensions. I don't think that's quite as intuitive for these variational autoencoders. At least I don't know of a straightforward route to be able to identify that. And to my knowledge, it's more so this more trial and error approach. I will say that if we were to do this inverse design process where you fit a latent space then to a machine learning model, if that latent space is very high dimensional, I think you would lose some of the intuition of finding what like property maps to a low dimensional space. But I wouldn't say there's like this, I guess to answer your question more directly, I don't know of a route to like more directly measure the minimal latent space dimension necessary to make the most optimal VAE model. It's also the case that because the output metric of like how generalizable or how well things are reconstructed is a bit of a, it's not entirely objective, right? Because you might think like there's some level of like, I think this reconstruction is proper versus this level of generalizability for a certain chemical system, but it's not so much like a quantitative metric of which of the two that you want, depending on what the chemical system is or the real system of interest is. So it's hard to have like a quantitative optimization route of identifying that latent space dimension. That's like certainly one of like the tougher challenges of this type of an algorithm for sure though. These are great questions, by the way. I think these are deep and asking about these. I think this is a very like complex machine learning algorithm. It's not very easy to understand, especially if you dig into the background math of it. So I'm glad y'all are thinking very deeply about all these fundamentals. Happy to answer any other questions along the way. Otherwise, I know there's like a wrap-up session coming up. Also, any other questions we get regarding the whole not just this particular example, other all the other dimensionality reduction stuff we went over yesterday. Anything else, happy to chat with you in the last few minutes. All right, well, if there's no other questions, I think I'll pass it back to Sapna and Niraj. But it was just a pleasure to be able to teach in this, and thank you all the students for attending and asking wonderful questions. And happy to chat if we're ever at some conference or anything. Please come up and say hi.
Thank you, Shuwen, for the session. You did a marathon. And thank you for all the instructors and all the students who have participated. So with this, we come to an end of the workshop. All the material, as you guys know, is on GitHub, and the videos have also been uploaded and will continue to be uploaded for today and yesterday.